So let me start my lightning. It's not supposed to be what you see on the schedule because Habra Habra blog post was exactly about that, and I don't see the reason why I should just repeat everything. Instead, I will talk about the tool which we developed at Sourced. It's called Hercules. So let me start. So the goal of this tool is to create line burn down charts. What it means is that when you develop software, some of your lines expire because they are overwritten through time by other commits. And it's very interesting to see how many lines are still alive throughout the time. So in this example, you have like some abstract file foo.py, and you have 3 years, 14, 15, 16. Initially, you had 3 lines. Then you had a comment which inserted 3 lines in the middle. And 2016 commit, it renamed the class, so number line is no longer alive. It removed question mark, inserted 2 lines here. So the line burn down chart would look like that. So at day 0 you have 3 lines. Then, well, we have kind of a linear approximation, and by 2015 you have 3 lines inserted this year and 3 lines still alive. And finally you have 2 lines from the first year, second year, and 3 lines from the last year. This is called a line burn down chart. We are not, the first ones who invented this type of chart. The first, I think the inventor was Eric Bernardson. You may know him because he is one of the authors of Luigi, a very popular Spark and Hadoop workflow manager. So he created a blog post about Git of TCUs. It's basically a Python script which calls git blame along all the commits in a repository and creates this nice line burn down. He evaluated his tool against like 10 very popular Git repositories, and it turned to be really useful, and you can draw interesting conclusions from it. The only problem is that this tool is slow, and we decided to create our own using GoGit engine. It's open source, like Git implementation using Go language. So we wrapped it and created Hercules, and we have a blog post about it. So there are 2 problems you need to solve if you want to develop such kind of a tool. The first is that I need to define a root along with you are going to diff files. Git is not a linear structure. Git has branches. Branches can merge, and sometimes it's very confusing. And yeah, the second problem is, of course, performance. If you take Linux kernel, it's really tough to analyze everything in some reasonable time. So let's start with diffroot. You have the root commit here. You have last head commit here. So the algorithm is very straightforward. Our engineer, Alberto Cortez, has a really nice presentation about git blame internals. It's called How to Blame. I think it's 150 pages, so it's really considerable. So you start from the head, because initially you only have the reference to the head. You go back to the root, and after you do that, you remember this path, and you diff starting from root backwards. Sounds easy, right? But if you have branches, it gets messy. Because at commit H, you need to decide which way to go. And what's even more bad is that Git doesn't have, explicit branches. In Git, branches are just pointers, and the pointers move through time, losing history. So like somewhere here, the information about branch names is completely lost, and you have to recover it somehow. Well, so you can try to recover the names of the branches because there is a working heuristic. And the first commit is usually the master branch, the main branch, and the second commit, merging one, is usually a topic branch. But sometimes that's not the case, especially when people, merge the master to develop and then develop to master, not following any guidelines. It becomes very messy. And there are octopus merges when you merge more than one branch, and it's even worse here. So what we do, it's not an ideal solution. I think git blame does the same. So we just merge all commits at the point merge commit was created and treat it as a single commit. That way we lose some information about history in topic branches, but we survive and still able to do something. Regarding performance, Eric's script has quadratic complexity because git blame is linear through history, and we call git blame on every commit, again, number of commits, and this is why it's quadratic. We can reduce it to linear complexity if we apply incremental blaming. The problem is that incremental blaming is not possible using public APIs of libgit2 or cgit or whatever tool you use, because it breaks some abstractions. Luckily, GoGit was designed for this sort of stuff, hacky things right from the start. We designed it to provide as more flexible solutions for analytics as we could. So we have really nice diff tree algorithms there, which compares file trees. We have really nice ordinary diff there, and we were able to use it in our tool. Well, when you figure out how to diff files and which files to diff, there is still a problem. How do you store the line intervals? The first and most obvious, approach is to use a single linked list. So this is line number 1. The length is 1. Then you have one line from 2014. Then you have 2 lines from 2016, and so on and so forth. But there is a second approach, which is a balanced binary tree, where you put indices of starting lines instead of lengths. And you can infer the interval size by just subtracting this number from this number, for example. Each approach has its own pros and cons. Linked list is very easy to maintain, very easy to code, but the complexity of finding the next file offset is linear, obviously. In balanced binary tree, it's very easy to locate new changes, but sometimes it's costly to update everything. It never leads to complete restructuring of the tree, because if you insert something or delete something, you just go subsequent nodes and reduce or increase the keys. You do not rebuild the whole tree, but you still have to balance it sometimes, and it takes some complexity. What's good about the balanced binary tree approach is that you are very often dealing with these sort of commits where you have one line deleted, one line added. So when you delete a single line or 2 lines or whatever in a symmetric way, you just have a zero final balance of additions and deletions. In this way, you do not have to update the keys of all subsequent nodes in a balanced binary tree, and your insertion and deletion operation is almost constant time. So at best case, you find the offset in logarithm time and updated in constant time, which is really good. Anyway, I think it's more like, a matter of taste, and we decided to choose the binary tree approach. It's a bit, more complex to code, but let's see how it behaves. Actually, it's not a bottleneck, so it doesn't matter after all. The real bottleneck is that we need to differ ourselves. As you may know, Git doesn't store commits as differences between files. It always stores snapshots. So it provides an abstraction of commits as snapshots. And this means you have to, difference files by hand. And, well, it really matters how fast you do that. There are not so many efficient diffing algorithms out there. The most widespread one is Myers. I think it's from 1980 something. It's very well known. The complexity is nice, but there is a problem that sometimes it's not, readable, and sometimes it doesn't really mean what the coder wanted to do. So you can, change several lines, and Myers diff shows that you did something else. The result is the same, but the way you achieve it, it's not what you intended it to be. This is why other diff algorithms were developed: patience and histogram. I think the complexity of patience and histogram is higher, but they are, more like a human readable way of diff. In our case, we just use analytics, so we can be a bit, imprecise, not so fancy. So we just take Myers. There is an implementation in Go, which is rather performant, and we use it. We tried to optimize diffing with CUDA, but we failed because diffing is very, branchy, and it's very data-driven, and it works really bad with single instruction multiple data approach. Let's try it. It's very easy. So you issue go-get, install Hercules, and you run it. So you specify a path to GitHub repository and pipe it to the supplied Python script, which does the graphing, and you get something like that for TensorFlow. Monthly burn down. So when TensorFlow was just released, not so many PRs, not so many edits existed. So for 1 or 2 months, it wasn't, hyped. Not so many people knew about it. Then it started to gain momentum, and some months were very, successful and received a lot of changes. But still, a lot of code which appeared at day 1 still exists, which means that the core architecture is, rather good, rather well designed, and it's not going to be outdated fast. In contrast, if you take, for example, AngularJS or other JavaScript framework, you will get completely different land burn down chart. I think it's not included here, unfortunately, but I can tell you that it's like rewrite everything every several months. And this means, the architecture is probably not that good, or there is something wrong with the programmers. You can change the plot type to relative so that it will occupy the whole space. I don't know what's better. Depends on your taste. And the tool is actually able to run the analysis on Linux kernel. It requires only 2 hours. I think 20 minutes goes to complete cloning. And it wants, well, considerable amount of operating memory size. You can optimize it by reading the repository from file system, but because GoGit, it's not perfect, reading a repository from a file system usually is slower, and I think the estimated time would be 20 hours instead. This is how it looks like. So Git started to be using Git in 2005. Since then, only 1/2 of the code was nuked. Still a lot of code is alive. And we have like good years here, a lot of contributions, and we have not that good years. So it looks rather stable, and we can draw the conclusions that, yeah, it's good architecture, and there will be no, revolutions as in JavaScript frameworks. In the future, we want to turn these plots into some metric, like survivability metric, which should correlate with the overall architecture quality, I guess. We would like to do that per developer, per file, and per directory. And as soon as we do that, we will kill per 6-ray engine because it does exactly that. Thank you.
Have you thought about doing this at a module level in addition to doing it at a project level?
Sorry, what level?
Of modules within one of the projects.
Modules. Yeah, exactly. So yeah, we would like to do that, like directory, file, module. Yeah. I guess if you do it per file, you can group files by module and get the same result.
Do you have some kind of understanding how to measure the quality? Because it makes sense when the code doesn't change so frequently, but for example, how to measure it?
You mean this survivability metric, right?
Yeah.
Well, again, we are not the first ones who invented. Whoa, what happened?
I'm unplugging you.
Okay, so it's very easy to create a label data set, just manually curated list of, I don't know, let's say 100 repositories, and just define that, okay, this threshold, everything above the threshold is good, everything above the threshold is not good. Eric had this kind of metric proposal. We need to, revise it and see if it goes well with what we want to achieve.
Maybe it's another suggestion that probably it can be, it can explain something about development process. They apply some pull requests. Probably they don't review.
Yeah. This is why we want to do that per developer and probably even per pull request. I think it will take quite a lot of resources to do it per pull request, but it would be a really useful metric. Yeah. Especially for Java, I guess. More questions?
Can you upload JavaScript picture, please?
Upload?
Yeah, JS frameworks.
Yes, actually, if you go to Eric's blog post, it has these pictures. We are not, doing something really different, so we will get exactly the same pictures. You can upload them yourself if you want. It takes like 5 seconds. But if you want it right now, just follow the link and get them on his blog post.
Okay, thank you.
Thank you.